Dear audience, welcome to the next session here. We have two wonderful talks ahead of us. This session has been sponsored by Google Quantum AI, by the way. Each talk will have a duration of 25 minutes. You can ask your questions during the talk already via Slack. Don't be disappointed if we don't pick them up at the time where you ask them. We will most likely postpone questions to after the talks. And please note that there are also the roundtables after the talks where questions can be answered. Okay, now I come to our first talk, which is on a new quantum Rényi divergences and their applications to device-independent cryptography and quantum Shannon theory. Our speaker will be Peter Brown. Peter, the stage is yours.
Thank you. You can hear me and see the slides fine?
I can.
Great. Okay, so yes, so this talk is going to be split into two parts. So it's going to be based on two separate papers. And in both of those papers, we'll introduce new families of Rényi divergences, which will be defined via a convex optimization problems. Okay, so in part one, it's going to be based on this paper here, where we introduce a new family of divergences and we show that they can be applied to compute lower bounds on the rates of device-independent protocols. So we know that in standard Bell non-locality setup, if we violate a Bell inequality, we know that the outputs of the devices have to contain some randomness. So we can use this observation then to build so-called device-independent cryptographic protocols based on these Bell inequality violations. So for example, we can build randomness expansion protocols or key distribution protocols out of this setup. However, the security and analysis of such protocols relies on us being able to compute the rates of these protocols. So for example, the number of key bits we can generate per input and output pairs of the devices. So that from the cryptographic perspective, we might think of the picture a bit like this. So the honest party's devices now are in some secure laboratories, and in order to violate a Bell inequality, they'll share some entangled quantum state and perform measurements on that state. But we might also assume for security reasons that maybe this entangled state was also entangled with some adversary system who keeps this state in some quantum memory. So when we compute the rates of these protocols, we want to say how much randomness the honest parties are producing from the perspective of some adversary system. So the asymptotic rates, for example, of randomness expansion protocols and QKD protocols are given here. So they're in terms of the conditional von Neumann entropy. For example, here we have the conditional von Neumann entropy of the outputs of the devices conditioned on the adversary side information. And I should also mention that the non-asymptotic rates can also be expressed in terms of these quantities here. So in order to compute lower bounds on the rates of these protocols, what we want to do is compute device-independent lower bounds on these conditional von Neumann entropies. So what does it mean to compute a device-independent lower bound? Well, we want to compute lower bounds in an optimization of this form here. So we have an infimum over conditional von Neumann entropies of the outputs of the devices conditioned on the adversary's information. We want to compute this infimum over all possible devices that obey some linear restrictions on the probability distributions that they have. So for example, this constraint here could just be some Bell inequality violation. And it's device independent in the sense that we want to take this infimum over all possible finite dimensional states, all possible measurements the devices could perform, and all possible Hilbert spaces on which those states and measurements might act. Now, this problem is quite large, and in general, it's quite difficult to solve. First of all, it's non-convex. And second of all, a priori, we don't have a bound on the dimension of these Hilbert spaces. So we restrict them to be finite dimensional, but we don't actually have an upper bound on the dimension that's required to achieve this infimum. However, there are still some approaches in order to solve this problem or get lower bounds in this problem. So for example, in this paper here, the authors looked at the CHSH game, and they were actually able to solve this optimization exactly for devices that had some CHSH score here. They got analytical bounds, and these were tight bounds. However, the techniques that were required in order to prove these bounds are sort of restricted in their applicability to other protocols. For example, they relied on the fact that the devices had 2 inputs and 2 outputs. Alternatively, one can compute numerical bounds via the min entropy. So by replacing the conditional von Neumann entropy here with a conditional min entropy, the resulting optimization is actually quite easy to a lower bound in a device independent way. However, unfortunately, the min entropy can be a lot smaller than the von Neumann entropy. And so such a method tends to lead to quite poor bounds. In just a couple of years ago, there was a recent work where the authors looked at deriving some non-commutative polynomial optimization problem whose objective would be always a lower bound on this optimization problem here. And in the paper, they did some numerics and it led to quite good bounds. However, their method is quite computationally intensive. So in this work, what we want to try and do is get the best of both worlds. We want to have something that's both easy to compute and leads to relatively good bounds. So our approach to this is actually to define some new conditional entropies that are by construction easy to bound in a device independent way, and all should be lower bounds on the conditional von Neumann entropy. So we actually define these conditional entropies via a more general quantity, in particular a divergence. And whenever you have a divergence, you can define, for example, these 2 conditional entropies from this quantity. And this is what we'll do. Okay, so the definition of our divergence, it looks a bit complicated, but the exact definition doesn't really matter for the purpose of this talk. But I'd like to highlight a couple of features of the definition, which I do think are quite important. So for example, this is a family of Rényi divergences. However, usually you would have a continuous family. So this family parameter would be a continuous parameter. However, we actually need to define it for a sequence of alpha. And this sequence begins at 2 and it tends towards 1. Secondly, sort of the novelty of these 2 works that I'm presenting here is that the divergences are not defined explicitly via some formula of rho and sigma, but instead they're actually defined as solutions to some optimization problem. And in particular here, this optimization is going to be a semi-definite program. And for the device independent applications, there are really 2 features of this optimization problem that are important. So first of all, the objective function is linear in rho and sigma. And secondly, the structure of the optimization is independent of the dimension of rho and sigma. So as we change the dimension of the states or the operators, the structure of the problem, the constraints that appear don't change. And this is very useful because when we do our device independent optimization, we want to optimize over all possible dimensions, and we don't want the structure of the problem to change as we do this. Okay, and we're happy to call these things Rényi divergences because they satisfy properties that we'd expect Rényi divergences to satisfy. So for example, when everything commutes, we recover the classical Rényi divergence. They also satisfy the data processing inequality. And they lie between sort of extremal families of divergences, namely the sandwich divergences and the geometric divergences. And in particular, this inequality here will tell us that the conditional entropies we define will all be lower bounds on the conditional von Neumann entropy. Secondly, we also have that as we decrease alpha from 2 down towards 1, the divergences will not increase. And so for the corresponding conditional entropies, the conditional entropies will not decrease. And so this means that we can hope that as we move through the family, we get improving lower bounds on the conditional von Neumann entropy. So as I mentioned, we use these divergences to define a conditional von Neumann entropy by the formulas I presented earlier on. And when you do this, you'll end up with a definition that looks like this. Again, the exact definition is not too important, but the main thing here is we still have the features that we wanted in order to perform the device-independent optimizations. For example, the objective function is still linear in this row, and the structure of the optimization doesn't depend on the dimension of the states. Okay, so I think it's maybe a bit nicer to look at the simplest example rather than this big general definition. And so this is for the 2 entropy in our family. So if we look at this 2 entropy definition, we can compare it with the min entropy definition when it's defined via this optimization problem here. And we know that the min entropy is easy to bound in a device independent way. And actually, when you compare these two optimization problems, you see that they're very similar in their nature. So they have very similar constraints and similar objective functions. And in fact, everything that makes the min entropy very easy to optimize also translates into this 2 entropy, and the 2 entropy is very easy to optimize in a device independent way. And similarly, this goes on through the family of divergences. And yes, and actually these 2 entropies are in fact connected. One can show that via an appropriate Cauchy-Schwarz inequality on this objective function here, one would actually basically recover the min entropy. And this Cauchy-Schwarz inequality tells you that this 2 entropy can never be smaller than the min entropy, for example. And so for our device-dependent applications, we'll follow the exact same procedure that you would when you wanted to optimize this min entropy here. So in the device-independent applications, this state here will be a classical quantum state that encodes the classical outcomes of the honest party's devices that's correlated with the quantum side information of an adversary. And you can then, once you have this set up, you can then rewrite everything, this optimization, in terms of the initial entangled state that was shared between the devices and the measurement operators that were used by the honest parties. And once you've done this, you can then optimize these conditional entropies fairly straightforwardly using the NPA hierarchy. And so we did this in the paper, and we looked at the rates of both randomness expansion protocols and QKD protocols. And we looked at the rates when we constrain the devices by some full conditional probability distribution. And so this is the most amount of information we can collect in the device independent way. So hopefully this will lead to the best rates, is the idea. And we also assume that the devices have inefficient detectors to make the plots a bit more experimentally relevant. And so what this means is with some probability eta, the device will measure correctly and output the measurement result. And with some probability 1 minus eta, the device will just fail, and we'll just record this failure as the outcome 0. Okay, so when we looked at the rates of randomness expansion protocols, we got a plot like this. So we compared the rates for a couple of entropies in our family with the min entropy. We compared it with this analytical bound for the CHSH game that I mentioned earlier, and also this non-commutative polynomial bound that I also mentioned in a previous slide. And what we found is that the entropies in our family were all quite a big improvement over the min entropy, and they also improved over this CHSH bound here. And for high detection efficiencies, we found that these gave the best rates. However, for randomness expansion, we found in the lower detection efficiency regime, our bounds were actually outperformed by this non-commutative polynomial technique. For QKD, though, we found some quite nice results. So again, we compared some entropies in our family with the min entropy, and we compared it with this analytical bound for the CHSH game. And for QKD, I think the thing to look at here is exactly where these rate curves cross to 0. Because when this tells you the minimal detection efficiency you need in order to actually perform QKD. So if we zoom in on the bottom left corner, we see that, so as we move through the family of entropies, we get increasingly better rate curves. And what we see is previously for the sort of standard DIQKD protocol, the best known bound was this red curve here based on the CHSH game. And we see that at least for the 4/3 and 8/7 entropies in our family, we get improved rates and we get new minimal detection efficiency requirements for DIQKD. Okay, yes. So now I'd like to move on to part 2. And part 2 is going to be based on this paper here by Hamza and Omar. In this paper, they introduce, again, a new family of divergences, and we'll give some applications to, for example, channel discrimination protocols. So we've already seen in part 1 of the talk that that divergences are useful quantities. We use them to define some conditional entropies that we could apply to compute the rates of randomness expansion and key distribution protocols. And divergences also find their own sort of direct operational meanings in terms of rates of, for example, hypothesis testing protocols. And there are many families of divergences out there. Some will be good for certain applications and others for other applications. So in this work, we're going to introduce, again, another new family of divergences, these D-sharp divergences. And whilst these D-sharp divergences won't themselves find some operational meaning in the terms of rates of some protocol, they will turn out to be an extremely useful proof tool for proving properties of these sandwich divergences. And these sandwich divergences are an extremely useful family of divergences, and they found a lot of applications both in quantum information theory and in quantum cryptography. So let me give you the definition. So this is defined, it's going to be defined in terms of this weighted matrix geometric mean that we saw in Hamza's tutorial on Saturday. So the definition of the divergence is given here. And one thing to note is that it's actually defined here for a continuous family. So we have a definition for all alpha greater than 1. And it's defined in the usual way as 1 over alpha minus 1 log of some q quantity. And like in the first part of the talk, this q quantity is going to be defined via a solution to a convex optimization problem. And this convex optimization problem is this problem here. And one thing to note is that this is actually a semi-definite program when alpha is a rational number. And this follows again from something Hamza mentioned in his tutorial, namely that this weighted matrix geometric mean for certain values of alpha is can be represented via some semi-definite constraints. And another thing is that actually when alpha is 2, this definition actually coincides with the iterated mean divergences that I mentioned in the first part of the talk. And so for our applications, I think it's useful. Well, it's going to be useful to define what's known as a channel divergence. So you can define divergences not only for states, but also for channels. And you can do this in the standard way. So you have 2 channels, N and M, and you look at their action on 1/2 of some state. And then you take a supremum over all possible states, which you can think of as the supremum is trying to maximize the distinguishability between these 2 channels. And for the D-sharp divergences, you can actually absorb this supremum into sort of the definition, into the optimization that defines the D-sharp divergences. So so you can reformulate this channel divergence for the D-sharp divergences again into some convex optimization problem, which takes a similar form to the definition for states, where here we have the Troy matrices of the channels. So we have a similar constraint to what we had before. And in the objective function now, we just have this infinity norm. But we still have, in fact, for when alpha is rational, this is an STP. So we can still compute this quite efficiently. Again, we're happy to call these things a family of Rényi divergences because they will one can show they satisfy the various properties that you'd expect a family of Rényi divergences to satisfy, the data processing inequality, and in between these 2 extremal families of divergences. And finally, the D-sharp divergences have kind of this special property that they regularize to this sandwich divergence. And this connects these D-sharp divergences to the sandwich divergence. And this connection we can then exploit in order to use these D-sharp divergences to prove properties about these sandwich divergences. So I'd like to go through 3 applications of these D-sharp divergences now. And so for the first application is going to be to actually computing this quantity here, which is the regularized sandwich channel divergence. So it's expressed as this formula here. And this quantity comes up, for example, in rates of channel discrimination problems. So it's a useful quantity to be able to compute. And actually previously it was not known whether this quantity was even computable. But however, using the D-sharp divergences, one can not only show it's computable, but that we can actually get a method to compute this quantity to an arbitrary accuracy. So basically in the work, what is shown is that one can compute a sequence of improving lower bounds and a sequence of improving upper bounds that coincide as m tends towards infinity. And these lower bounds and upper bounds are defined in terms of the D-sharp channel divergence between the mth tensor powers of the channels. So we can compute these quantities and compute to whatever accuracy we want these regularized sandwich channel divergence now. Another thing to note actually is because these sandwiched channel divergences are upper bounds on the relative entropy channel divergence, you can also compute, use these D-sharp divergences to compute bounds on this relative entropy relative entropy channel divergence. Yes, and so for the second application, we have a new chain rule for the sandwich divergences. So this chain rule looks like this. So if you have two operators, rho and sigma, and two channels, n and m, and you look at the sandwiched divergence of the channels applied to the operators, you can actually upper bound this in terms of a divergence of the channels and a divergence of the operators. And so one can see this as a generalization of the data processing inequality. So for example, if n is equal to m here, then this term will vanish and we just recover the data processing inequality. And this same chain rule was actually already known for the relative entropy. And so this extends this chain rule now to the sandwiched alpha divergences for alpha greater than 1. And maybe one example of why this might be useful is for maybe you have a repeated channel application. So for example, if this n to the power of t denotes the channel n composed with itself t times, we can upper bound this divergence, which if t is very large, may be quite difficult to compute. We can upper bound this divergence in terms of just t times the regularized sandwich divergence between the channels and this divergence between the operators. And we know from the first application that we can compute upper bounds on this quantity as well. So we can use the D-sharp divergences again to get another upper bound on this quantity. Finally, the third application I'd like to mention is that to channel discrimination problems. So in channel discrimination, you are given your promise that you're going to receive one of two channels, n or m, and you're asked to determine whether you received n, given black box access to this channel. And so our recent work cited here is they introduced a quantity known as the amortized divergence. And they showed also that this amortized divergence was a useful tool in order to compute rates of the channel discrimination problem. And actually using the chain rule on the previous slide, one can show that the amortized sandwich channel divergence is actually equal to this regularized sandwich channel divergence. And what we also know from the first application now is for arbitrary channels n and m, we can compute this using the D-sharp divergences. And what this means is that these D-sharp divergences then allow us to compute bounds on these channel discrimination protocols through this equality here. Another thing that came out of this is actually one can show in certain new regimes that the adaptive strategies for the channel discrimination problem don't help. And for those of you who know about these things, this new regime is actually the strong converse exponent regime. Okay, so I'd like to wrap things up with some further work and some open sort of problems. So from the first part of the talk, it would be nice to know if we can use these divergences, maybe apply them to different device-independent tasks to also compute the rates of those things. One thing, so in the QKD plot, we saw that these divergences gave improved bounds on this, improved detection efficiency thresholds for the sort of standard DIQKD protocol. But last year, there were a couple of papers that introduced a sort of modification to this protocol. They introduced an additional step that allowed them to show that for the CHSH game, one could improve this red curve again. And so we didn't analyze this adapted protocol in our work, but it would be nice to see if we can also analyze this additional step in the protocol with our conditional entropies in order to try and further improve these QKD thresholds. Another thing is that I didn't mention, but the techniques that these divergences that we introduced, or the conditional entropies, can also be applied to the entropy accumulation theorem to actually prove security of the corresponding protocols. And so you can get actually finite round rates on these protocols. It would be nice to actually try and compute these things and maybe try and analyze the feasibility of a real device-independent DIQKD protocol with the current technologies. Something else for both parts of the talk is whether or not we can make the computations of these divergences more efficient via symmetries, or in the device-independent case, maybe by using some dilation theorems. Something else that's open is that we don't actually know what the limiting cases of these divergences are when alpha tends to 1. It would also, so in the paper that goes into the second part of the talk, there are some additional applications to the sandwich divergence, and whether there are more applications would be interesting to explore. And finally, it would be nice if we could, we've seen that defining divergences via complex optimization has been quite fruitful, and whether we can define further divergences with different applications will lead to future work. Thank you for listening, and I'll leave you with some references for the talk.
Many thanks, Peter. Many thanks. I got a bit worried regarding the time, but Omar has been answering questions on Slack while you were talking.
Great.
Many thanks to you, Omar. I think this is a good way of making these online talks a bit interactive. So that there are not too many questions. Maybe, so I have one myself, but I can also ask it later. So let me pick one from Slack here, okay? So Sue Cow is asking, what is the intuition that this type of quantum Rényi entropy is better than the original quantum Rényi entropy? And I think it's a bit about the applications, if I interpret this correctly. So what are the better, what problem can you better solve using the new divergences?
So, okay, I can comment mainly on the device-independent side of things. So when you want to do these device-independent optimizations, the standard sort of divergences that we have out there, they're sort of complicated nonlinear functions of these rho and sigma. And what we really want is some optimization problem that has the same features as what we see in the min entropy, where we can write it as this, well, we can write the min entropy like a guessing probability. So we can really interpret it as the adversary sort of optimizes over measurements on that state. And the form of the min entropy makes it very easy to optimize via this NPA hierarchy. And so the reason that we sort of kind of develop these divergences in this way is really to kind of capture this structure of the min entropy. So it's kind of a custom built family of divergences that are super useful for the for device independent optimization. I mean, in general, actually,
Peter,
what one finds is that working with a sort of optimization form of these divergences, sometimes some of the proofs end up being quite easy, is also another advantage.
Thanks, Peter. We have to have an eye on the time.
Yeah, sure.
There's a lot more time at the roundtables for questions. So I hope it will be a lively discussion there. And now I would like to introduce our next speaker.